If we have a box with one or two particles in it, and we want to solve the problem, it's not too hard. We normally think of it as rather easy. One or two particles, the basic rules of momentum conservation, F equals ma, and so forth, we solve the problem. If we have a box with 10 to the 23rd particles in it, it's also easy. But easy, not in the same way. We use different rules. We use maybe a Stokes equation. We use hydrodynamics and so forth. We make the problem easy again. This is 10 to the 23rd. This is 2. It's the transition from one to the other which is hard. At some point, and I don't know where it is exactly, is it 50 particles? Is it 30 particles? Is it 150 particles? Somewheres in there, there's a transition from particle-like behavior, the simple particle-like behavior, to the smoother hydrodynamic behavior. I don't know. I'm not sure exactly where it is. I would guess it's somewheres around, for a small box like this, I don't know, 50 particles. With 50 particles, I would bet you can see swirling behavior. I would guess that you can see vortices and so forth, at least a bit. Somewheres in the transition between here and here, there's something interesting happens. And it's that interesting thing which is hard to quantify. That is where we need computers to tell us what's going on in this region here. Okay, I think the same exact thing is true, or something very, very similar to it, in thinking about the relation between quantum mechanics and gravity. On the one hand, if I have 2 qubits, I can entangle them, and in some very, very vague way, we can say that's a proto-wormhole, but we don't think of it that way. We just think of it as 2 qubits entangled. We can do quantum teleportation, but we don't think about it as going through a wormhole. On the other hand, if we have enough qubits on the side, entangled with enough qubits on this side, we begin to think that there's a geometry to it, a smooth geometry. The smooth geometry is some kind of wormhole. And somewheres in between, or somewheres, some number in here, it could be 100 qubits, 1,000 qubits, I don't know exactly where it happens, there's presumably a transition, not a sharp transition, a sort of qualitative transition let's call it quantum mechanics or simple quantum mechanics to quantum and gravity behavior in this smooth sense here. Where is that transition? How do we get at it? How do we quantify it? How do we think about what goes on in this transition? Probably that is as hard as anything, and that is where I think the first quantum computer studies of these things can happen. In this region in between here with 50 qubits, 25 qubits, 100 qubits, I don't know where it is exactly, but that's perhaps where, with small quantum computers, where smallness may be a virtue. Smallness may be a virtue because we get to see what happens in between these two. Are there situations in which we really want smallness? And I think there are. For example, what does happen at exponential times? The things that were being discussed here a moment ago have to do with black holes. Again, we'll draw that picture. Black holes grow with time. The distance between the two horizons, these are eternal black holes. But the real question, or a real question, a really interesting one, is what happens at exponential time when computational complexity tops out, can't be any bigger than that. That is where we think the standard general relativistic, ordinary classical rules of gravity break down. But we don't understand how it breaks down. We don't understand what really happens. It may be firewalls, it may be something else, we don't know. Okay, what do we do? Well, perhaps quantum computation can help us, but we don't want n to be large. Why don't we want n to be large? Because we don't have to want to go to timescales which are e to the n, where n is large. So this is exactly the place where I think that smallness, or relative smallness, may be a virtue, and asking in the transition region here, what happens when we get to exponential times, where exponential may be no bigger than e to the 5. It may be that smallness is a virtue that allows us to address questions that
that we might not even, if we had these giant quantum computers that could do 10 to the 23rd molecules, we may never have thought of these interesting questions in between.